Alright, so today I'm going to explain how an equation works.
And the equation I'm going to explain is this. The initial velocity equals the square root of negative 4.9 times the change in the x direction squared all over the cosine of the angle squared times the change in the y direction minus the change in the x direction times the tangent of the angle. Now, this doesn't make a lot of sense to you now, but hopefully by the end of the video it will. I don't know the exact name for this. Presumably there is a name for this equation. I doubt I'm the first one to come up with this. But I didn't actually learn about this equation itself. I more arrived at it through physics homework, and we haven't named it yet. Now, you're probably wondering, well, what is this equation used for? And it is used to figure out at what velocity you should launch a projectile at a set angle to reach a set point. Now, an example for this is, say you have your potato cannon right here, and you want to hit a target right here. Well, you know how far away it is along here, and you know how far away it is along here, and you have it set at a specific angle, so now you want to figure out, alright, what speed should I launch it at, so it hits that target. That is what this equation is used for. Now, before I get into the math of it, I'm going to explain the variables. We have v sub o, v sub ox, v sub oy, delta t, delta s sub x, delta s sub y, and theta. Now, v sub o is the velocity you'll be launching the projectile at. This is what we're solving for. V sub ox is the horizontal velocity that the object is going at. So, if it's going up like this, v sub ox is how far like this it's going. And v sub oy is how far this it's going. It is the vertical velocity the projectile is going at. And then delta t is the change in time, or how long it would take the projectile to get to the target. Now, we don't end up having these three in our equation, but we do need them to get to our equation. And delta s sub x is how far away it is along the x direction. So, in my example, it was this. And delta s sub y is how far up it is. Again, in my example, it was the y. And theta is the angle that we have the potato cannon at. Now, our equation is essentially a combination of two equations. One, to figure out how fast we need to travel in the x direction, which is that, and one to help us figure out how far we need to, or how fast, we need to travel in the y direction, which I am writing right now. It's a bit longer. That. And I will explain both of these. Now, to figure out how fast we need to travel in the x direction, we have this. And not that complicated. Velocity is a distance over a time. For our example, we're going to do meters per second. And velocity is whatever meters per second. So we're just taking the distance we traveled and dividing it directly by the time it took. Not that complicated. Now, finding how fast we need to go in the vertical direction is a bit more complicated. And for that, we have this equation. And you'll notice the a here. That stands for acceleration. And since we're on Earth, we know what that is. And that is negative 9.8 meters per second squared. That's the effect of gravity on the Earth, or the acceleration. And that times 1/2 is negative 4.9. And I'm just going to leave it at that. Since I've now illustrated the point, I'll just cut out that step. And you'll also note that it's meters, so your distances need to be in meters, or else you won't get the right answer. Now, this whole long equation is essentially derived from two other equations, which are the acceleration equals the final velocity minus the initial velocity all over the change in time. Now, the final velocity minus the initial velocity is the delta velocity, or change of velocity, and this is similar to the delta s, or the change in position or distance, and that is, the final position minus the initial position, and that gives us how far it traveled, or the distance. Same concept with the velocity. It gives us the change in velocity, or the velocity that's changed. You should understand it. And the other equation we have is the initial velocity plus the starting velocity over 2. That equals delta x over delta t. And you'll notice that that is similar to the equation used to figure out the horizontal velocity. And that's exactly what this is. This figures out velocity. And what it actually figures out is average velocity. Hence the final velocity plus the initial velocity over 2. That's used to figure out an average. The reason that we don't need this section there for the horizontal velocity is because gravity doesn't affect the horizontal velocity. So the final velocity and the initial velocity are the same. That means the average velocity is the same as the initial velocity. So we go ahead and just write it as the initial velocity, so we don't have all these other variables. Now, because I want to explain everything, I have the first step to figure out the equation to figure out our initial vertical velocity. And what we have is we have our first equation, where acceleration equals the change in velocity, or the final velocity minus the initial velocity, over time. And what I did for this is I multiplied time to each side, so these times canceled. So now we have the acceleration times time equals the final velocity minus the initial velocity. And then I added the velocities to both the initial velocity to both sides, so these velocities canceled. So now we have the acceleration times time plus the initial velocity equals the final velocity. And this math all checks out, so I can assure you this equation is accurate. Then, for a second equation, which was the average velocity, or the final velocity plus the initial velocity over 2, and that equaled the change in position over the change in time. So what I did is I multiplied 2 to each side, so these 2 cancel. So now we have the final velocity plus the initial velocity equals 2 times delta x all over the time. Then I subtracted the initial velocity to both sides, so these velocities cancel. So now then we have the final velocity equals 2 times the change in position over the change in time minus the initial velocity. And since both of these equations equal the final velocity, I can set them equal to each other and then solve from there. So for the second part of it, I set the two equations we got earlier equal to each other, because we could do that. And then I added the initial velocity to both sides, so these two initial velocities cancel. So now we have the acceleration times time plus 2 times the initial velocity equals 2 times the change in position over the change in time. Then I multiplied the change in time over 2, so the 2 and the change in time canceled, to both sides, and I distribute it, so I would then get 1/2 a times time squared plus the initial velocity times time equals the change in position. And since all this math is, again, accurate, that is how we got the equation. So, hopefully, you now know how we arrived at this equation here. Now that we know how to get our vertical and our horizontal initial velocities using other variables, we can now figure out our combined velocity, the velocity we'll be using to shoot our potato out of our potato cannon. And that is why I've drawn this triangle, because we need to use some trigonometry. You guys are loving this equation, I'm sure. So what we have is, remember that sine of some angle equals the opposite over the hypotenuse. Well, the opposite is vertical, so that would be like the initial vertical velocity. And cosine of some angle is adjacent over hypotenuse. And adjacent is horizontal, so that would be like the horizontal initial velocity. And then this h would be our combined initial velocity. So, if we just substitute that in, we have the sine of theta equals the initial vertical velocity over the initial velocity. Multiply the initial velocity to there. So now we have the initial vertical velocity is the same as the combined velocity times the sine of our angle. That's how we do that. Similar thing with the cosine. We set the cosine, we set the variables equal, so we have the initial horizontal velocity, that, multiply it to both sides, and then we have the initial vertical velocity equals the cosine of some angle times the total initial combined velocity. So, we can now substitute the initial horizontal velocity for this, and the initial vertical velocity for this, which gives us one less unit. Well, it doesn't really give us one less unit, but it gives us a combined velocity and then the angle. Now we have yet another step. Going back to our horizontal velocity, which is that, we need to have it so it is delta t that equals. And what we do, we'll multiply delta t to both sides. So we have this, and then we just divide by the initial velocity, so we get delta t equal to the change in position over the initial velocity. And that is crucial because we need to do some substituting. Alright, now here we have our initial vertical velocity equation. And you'll notice there are gaps here, and you hopefully remember that time used to go in those. And in the previous segment, I had the horizontal velocity equation set equal to time. And since while the position variables and the velocity variables for each of them will be slightly different, the time will stay the same throughout this. So, since the time's the same, we can plug in our horizontal velocity equation, which was this for time. And then we can do some solving and have it so that the whole equation equals the initial velocity. Now we have our final step, and we have the change in vertical position equals negative 4.9 times the change in horizontal position over the initial velocity times the cosine of theta squared plus the initial velocity times the sine of theta times the change in horizontal position over the initial position times the cosine of theta. Now, you'll notice I have the trigonometric values in here, and I just went ahead and substituted the initial vertical and the initial horizontal velocities with their subsequent trigonometric equations, because just to cut out that step, because I didn't have room, as you may have noticed. Now, from there, we can simplify this. So, this part will stay the same, but we will now have, since these initial velocities cancel, and sine theta over cosine theta is tangent theta, we will have the initial vertical velocity equals negative 4.9 times the horizontal velocity squared over the initial velocity squared times the cosine of theta squared plus the initial horizontal velocity times the tangent of theta. I then subtracted the horizontal velocity times the tangent of theta, or the horizontal position times the tangent of theta to both sides, so these cancel. So we now have the vertical distance minus the horizontal distance times the tangent of theta equals negative 4.9 times the horizontal distance squared over the initial velocity squared times the cosine squared of theta. Then I multiplied the initial velocity squared to both sides, so these cancel, and I divided both sides by the vertical distance minus the horizontal distance times the tangent of theta. So I divided that to both sides, so these cancel. So we then have the initial velocity squared equals negative 4.9 times the change in horizontal position squared all over the cosine squared of theta times the change in vertical position minus the change in horizontal position times the tangent of theta. I then took the square root of that, and that is how we find the initial velocity if we are given the horizontal distance away, the vertical distance away, and the angle we have at our projectile launcher.
Now, yes, I'm aware that was a lot of information, so I'd encourage you to rewatch the parts that you didn't understand, even if that means rewatching all of it, because my goal here is to teach you something. And I also have something else. In physics, at least the level of physics I'm in now, we don't take into account air resistance. So this equation doesn't actually have any real-world applications. Just to let you know, so you don't try using it and become disappointed and think I'm a liar. But, however, if you find yourself in a vacuum tube on Earth or on the moon, then you can use it. So keep in mind, if you're on the moon, divide negative 4.9 by 6 to, because that's the ratio of the moon's gravity to Earth. So that way, then it'll be accurate. Yeah, hope you enjoyed it, hope you learned something, and see ya!